Hi everyone, my name is Christopher Kuhn, and in this video I'd like to present our latest research results, which we have published in the paper Pixel-Wise Failure Prediction for Semantic Video Segmentation. Semantic image segmentation is the task of classifying each pixel in an image as belonging to one of several semantic classes, such as car or pedestrian. One relevant application is the safety-critical task of autonomous driving. However, despite advances in the state-of-the-art, misclassifications remain inevitable. In order to avoid dangerous mistakes, failure prediction can be used. As an example, look on the right at the sample image from the Cityscapes dataset. At the bottom, you can see the pixel-wise errors made by the state-of-the-art Deep Level v3+ architecture. The pedestrian hidden between the cars is completely missed. Failure prediction can be used to detect these misclassifications and avoid any decisions that would endanger that pedestrian. In this paper, we propose to exploit temporal data to improve state-of-the-art failure prediction. We extend an existing approach with sequential input, and then we also use the sequential data to predict future failures of future frames as well. And finally, to properly investigate the proposed approach, we also create a new large-scale annotated video dataset for semantic segmentation. So, what does related work have to offer? Failure prediction can, for example, be approached using uncertainty estimation, such as variance-based methods like MC dropout or deep ensemble. Recently, introspective failure prediction has outperformed such uncertainty estimation methods for the task of semantic segmentation failure prediction. On the right, you can see a comparison of MC dropout, deep ensemble, and introspection for a given sample image. Introspection works by learning from previous errors, as shown here in green and red, and training a new semantic segmentation model to predict for each pixel either the class success or failure. As you can see, introspection produces a more accurate and smoother failure prediction mask. Regarding temporal information, convolutional LSTMs have been used before to improve the precision of semantic segmentation. This has also been used to extrapolate into the future to predict semantic masks for future frames. In our work, we propose to use those insights and apply them to failure prediction as well. So let's look at the resulting architecture of the proposed approach. Our goal is to extend single-image introspective failure prediction with temporal information. To this end, we add convolutional LSTMs to the baseline semantic segmentation model, in this case the Deep Level v3+ architecture, and train it with image sequences to output the semantic labels of the last frame of each image sequence. Then we freeze the encoder and train a second decoder, this time with the pixel-wise errors the trained baseline semantic segmentation model has made on the whole training set. This gives us error labels, which the second decoder uses as a ground truth to assign each pixel of the given image sequence input a prediction of failure or success. Next, we go one step further and try to use temporal information to predict future failures as well. For this, we use a sequence of the previous predicted errors as input for an encoder-decoder architecture. Then we have two options. We can train with the current ground truth error label to refine the current prediction. This way, we take the last 4 slightly incorrect predicted error maps and train to output the correct current error map. This way, this architecture works like a denoising autoencoder. The other option is to train with future ground truth error labels. This way, the model learns to extrapolate into the future and predicts where our pixel-wise failures will be in the future frames. This approach of using previous failure predictions to predict future frame failures requires frame-wise semantic ground truth maps in order to obtain frame-wise ground truth error maps. However, datasets like Cityscapes only have the semantic labels for the last frame of each sequence. Existing datasets that have frame-wise semantic labels like Cambit are severely limited in size, having less than 1,000 images. To this end, we introduce a new dataset, the densely annotated video driving DAVID dataset, a large-scale video dataset generated in the CARLA simulator. It contains around 11,000 images in a total of 28 video sequences in diverse weather, traffic, and daytime conditions. This allows to evaluate and test approaches like the proposed future failure prediction approach in a large-scale environment. So let's talk about the details of how we experimentally evaluate the proposed approach. For semantic segmentation, we use the established DeepLabV3+ architecture as a reference model. Since we want to learn from temporal data, we extend this architecture with convolutional LSTMs, as it has been done with other architectures in the state-of-the-art as well. As datasets, we use cityscapes, as well as the newly introduced DAVID dataset. For the failure prediction, we use two state-of-the-art baseline approaches: Deep Ensemble as the best performing uncertainty estimation method, and single image introspection, which has shown state-of-the-art performance for this task before. Then for the future frame failure prediction, we simply use the current frame prediction as a simple baseline predictor. This allows to investigate whether the future prediction offers any benefits, or whether we could simply reuse the current frame prediction as a rough baseline prediction. Finally, as a metric to evaluate everything, we use the area under precision recall curve. This is a scalar metric that considers the class imbalance inherent to failure prediction, where most predictions are of course successful and only few errors in total can be predicted. And this way we can easily compare all models and all approaches using a scalar metric. First, let's look at the results for the current frame prediction. For semantic segmentation, adding convolutional LSTMs to DeepLabV3+ immediately improves the performance for both the DAVID and the Cityscapes dataset, as it has been shown before in the literature for other architectures as well. Interestingly, the gain is larger for the Cityscapes dataset, which can be explained by the fact that the simulated DAVID dataset is easier in general, and the additional information from the temporal sequences offers less benefit, since one single image is already enough to achieve over 90% performance. Then we train the proposed approach to predict basically those 9 to 14% of errors made by the baseline model. We can see that the reference approach of Deep Ensemble, which isn't trained directly with any failure data, performs the worst for both datasets. The single image introspection outperforms Deep Ensemble, as it has been shown in previous work. And finally, the proposed approach that additionally considers temporal information again significantly outperforms single image introspection by roughly 6%, again with a bigger improvement noticeable on the Cityscapes dataset, which shows that the worse the baseline model performs on the dataset, the better the failure prediction can perform, since there are more failures to learn from. To better understand the failure prediction performance of the proposed approach, let's now look at some class-wise results of the proposed approach. For the DAVID dataset, we can see that the best performance occurs for the pedestrian class, which contains both people and bicycles with people on them. Less dynamic classes such as fence or wall are predicted the worst, which shows that the temporal information does not yield much additional information here, since those classes do not move. The same holds for Cityscapes. Here we show only the dynamic classes, where in general the failure prediction performance is the best. Most notably, the safety critical class of person is in fact predicted really well by both methods, achieving 87% area under precision recall curve on DAVID dataset, and for bicycles 85% on the Cityscapes dataset. This really highlights how the temporal information that is especially critical for moving objects like people or cars is really helpful for predicting misclassifications of the inspected semantic segmentation model. Finally, let's look at the results for the future frame failure prediction. We train our encoder-decoder architecture with a sequence of 4 consecutive failure predictions and use either the current frame ground truth errors or the future ground truth errors as labels. The baseline method of simply copying the current failure prediction ET decreases with each future frame, going from 60.6% from the current frame to 53% 5 frames into the future. Using the encoder-decoder architecture, we can see that for the current frame, just this additional step of refinement significantly improves the performance. Basically, the model is able to smooth out the failure predictions from those 4 frames to, again, significantly improve it. Then, when training with future frames, we can see that the model is capable of accurately extrapolating up to 5 frames into the future. For this, each individual time step into the future, a new separate model is trained just to predict this one time frame. And here we can see that even half a second in the future, we still achieve 64% area under precision recall curve, showing that we are able to accurately extrapolate this far ahead. Let's now summarize the key insights of this paper. Temporal information is essential in dynamic tasks such as driving, where it can be used to improve both semantic segmentation as well as the failure prediction thereof. Integrating temporal information into a state-of-the-art approach has improved it by over 6%. To investigate this approach, we have also introduced a new large-scale semantic video segmentation dataset called DAVID. While recorded in a simulation environment, we hope the promising results will inspire real-life datasets of this scale to be released in the future as well. Additionally, we have used the temporal information to predict the failures for future frames as well. For this, we have used insights from future semantic map prediction and applied them to failure prediction. Additionally, we have observed that this approach can also be used to refine the current frame failure prediction as well. For future work, an interesting idea would be to combine introspection with novelty detection. Introspection can only really predict failures that are similar to previously encountered ones. Novelty detection could allow to create a more comprehensive failure prediction for semantic segmentation. Thank you very much for watching. If you found this video interesting, feel free to visit our website to find further research results in the field of failure prediction. Also, if you have any comments, feedback, or questions, feel free to get in touch with us. We would love to hear from you.